Have you noticed a fascinating pattern in how we understand the world? When we were kids, we tried to make sense of things by asking, what is this? As we grew older, we began to ask, why is it like this? But if we dig even deeper, a far more critical question emerges. Under what structural constraints does it become what it is? This is what I want to talk about today, the high-dimensional structural theory. First, a note of clarification. This is not a strictly scientific theory. Instead, it is an interdisciplinary cognitive framework that helps us understand complex systems through structural relationships, information flows, and evolutionary rules. Modern science is already packed with similar ideas. Calculus and mathematics studies continuous change. Differential equations examine dynamic evolution under constraints. Topology focuses on invariant structures amid shape transformations. Graph theory analyzes relational networks. Probability theory uncovers patterns under incomplete information. In essence, mathematics does not study specific objects. It studies how structures represent the world. The same applies to physics. From classical mechanics to field theory and complex systems, more and more models no longer describe what objects are. Instead, they explain how energy flows, how systems constrain themselves, and how stable structures form. In this sense, physics increasingly becoming a structural science. Take artificial intelligence as another example. Many people view AI merely as a more powerful computing tool. But from a structural perspective, it essentially performs several core tasks. Input data is mapped into vector representations in high-dimensional spaces. These representations form embedding structures via transformer architectures. Attention mechanisms model information relationships. Diffusion models generate continuous structures through stochastic processes, and agent systems build closed feedback loops. From this angle, intelligence is more of an emergent capability arising within sufficiently complex structures. The logic extends to living systems too. The physical substance inside our bodies keep renewing, yet our individual identity remains stable over time. From a structural viewpoint, this continuity relies far more on neural connections, memory architecture, and information organization, rather than physical matter itself. Scaling further to industrial and social systems, corporations, cities, supply chains, energy networks, all are complex systems. Their long-term performance is rarely determined by isolated capabilities, but by information flow efficiency, feedback mechanisms, and resource allocation structures. Simply put, in most complex systems, long-term behavior is governed by structure, not local factors. It is important to emphasize that this structural perspective is not a unified ultimate theory. It is more of an analytical tool. Different disciplines support it in unique ways. Mathematics provides structural language, physics reveals structural laws, biology offers real-world cases of self-organizing structures, and AI delivers computable structural models. To put it rigorously, structure is one of the most vital abstract tools modern science uses to describe complex systems. Finally, why does the high-dimensional structural theory matter? Not because it gives definitive answers, but because it offers a brand new way of asking questions. We no longer only ask what happened. We ask, what structure made this phenomenon possible? Once you start thinking this way, you see not just surface phenomena, but the underlying constraints and evolutionary mechanisms behind them. This is the value of the structural perspective. It does not replace science. It brings us closer to the shared direction science is moving toward, understanding our complex world through structure.